Okay, in this video I'm going to talk about the reflections of a line passing through the orthocenter of a triangle with respect to the sides of this triangle. So, so basically the main theorem is that these reflections, these three lines, intersect at a single point, and this point lies on the circumcircle of this triangle. But so first let me give some background. So there is a related theorem that I proved in one of the previous videos about the reflections of the orthocenter itself. So basically, if we have an arbitrary triangle and we take the orthocenter of this triangle, so the point of intersection of the altitudes, then the reflections of this orthocenter with respect to the sides of the triangle lie on the circumcircle. So if we have this reflection, and this reflection, so the reflection of the orthocenter with respect to the three sides, then these 3 points, these 3 reflections all three lie on the circumcircle of the triangle. Yeah, so this is a well-known statement, and I proved it in one of the previous videos. So now what we have here in this theorem is that we take not just the orthocenter itself, but a line that passes through the orthocenter. So we take an arbitrary line that passes through the orthocenter, and we take the reflection of this whole line with respect to the three sides. So, and how we construct the reflections of a line. So we take, so let's say that we want, so let's call this line L, an arbitrary line that passes through orthocenter. So let's denote the triangle ABC. The orthocenter is H. These points, the reflections of the orthocenter, let's denote them by HB prime, HA prime, and HC prime. And so basically we take the intersection points. So like in order to construct the reflection of line L with respect to the line AC, one of the sides, so we take the intersection point. So the intersection point, so let's denote it by E. So like all the intersection points, so this intersection point is D, this intersection point is F. So when we reflect the line L with respect to AC, so the point E stays in place. So it stays, so E is mapped to itself, because it lies on the axis of symmetry, right? So like we reflect with respect to the line AC, and the point E is on the line AC itself. So it stays the same, and the line H is mapped to, the point H is mapped to HB prime from the theorem that I mentioned. So from these two, it implies that this whole line L, which is the same as the line EH, right? The line EH, this is the line L itself, is the line L itself. So this line L is then mapped to this line EHB prime, because a line is determined by 2 points, by any 2 points, and we constructed two points in the reflection, in the mapping of the line L. So therefore this whole reflection is just the line EHB, and like a line is mapped to a line always, under the axis symmetry. So EBH prime. So this line something like this. So this is the line. So, and the other 3 reflections are constructed similarly. So we take the intersection points of the line L. So let's call this line L, LB. So then we take the intersection points of the line L with another side, so with the side BC, let's say. So this is the point D, and we take the reflection of the orthocenter, so HA prime. And so DHA prime, this is the reflection of the reflection of the line L with respect to the side BC. So D is here. Yeah, and the third line, so this is, let's denote it L B, no, LA. And the third line is we take the intersection points with AB, F, and HC prime, the reflection of the orthocenter with respect to AB. So this is the line, this line. F, well, actually it so let's draw it slightly here, and then the intersection, yeah. So this is the line HC prime F, and the main statement now, the theorem is that the lines, so this is the line LC, and the theorem is that these 3 reflections, LA, LB, and LC, they intersect at a single point, and this point lies on the circumcircle. So we denote the circumcircle as omega, so then the theorem is that the lines LA, LB, and LC intersect at a single point and this point, or let's write, intersect at a single point which lies on omega, on the circumcircle of the triangle ABC. Yeah, so let's prove this. So the proof will be that we will consider it, so instead of considering the intersection of these lines, we consider the intersection of each of these lines with the circumcircle, and we'll prove that this is the same point. So in particular, we will calculate this arc between A and the point of intersection. So this arc that I highlight in blue, between the intersection points of each line and the point A. So this arc, we'll calculate that this arc is the same for all three lines, the measure of this arc. So let's introduce the... Okay, so let's draw another picture where these points would be deliberately different. So we have the circumcircle. We have orthocenter, reflections of the orthocenter. We have an arbitrary line. Passing through the orthocenter, something like this. And so this is E, HP prime, A, B, C, H, H, A prime, here's H, C prime, so we denote the angles of the triangle as alpha, beta, gamma, and we denote also the like this angle as phi, the angle between the line L, so this is the line L, and the side AC. So we now we construct this line. So this is the line L, LB. So let's denote this point as X. The second intersection point of this line LB is the circumcircle. So from the symmetry, so because this is symmetric, right, we know that this angle is also phi. So the angle AEX, right, is also phi. Then this, because it's an altitude, so this angle is 90 degrees minus gamma from this right triangle, right? One of them is gamma, the other is 90 minus gamma, and then this angle is also 90 minus gamma because of the symmetry, right? So now we have the arc. We know that the arc is equal to twice the inscribed angle that subtends this arc, right? So the arc HB prime C, this arc, is equal to twice the angle, the inscribed angle CA HB prime that subtends this arc. And we'll also use the statement, like a well-known fact about the angle that intersects a circle. So this kind of angle, it can be calculated from the arcs that it cuts from the circle. So if this angle is let's say phi, and this arc, so if this is the ABCD, then phi is equal to 1/2 of the arc the difference between the arcs AB minus CD. And if we have the vertex of the angle inside the circle, so something like this, then this angle is equal to half of the sum of these arcs. So in this case, phi is equal to 1/2 of AB plus CD. So these are two well-known theorems. I believe I proved them in one of the previous videos. So we will use them here. So here we have this angle phi that cuts two arcs H prime C and AX from the circle, right? So let me highlight these two arcs, this arc and this arc. So because of this, phi is equal to 1/2 of the arc HB prime C minus, yeah, so first we take AX minus HB prime C, and this we can HB prime C we already calculated, so we can write that this is equal to 1/2 AX minus 1/2 of H prime C, and H prime C is this, so 290 degrees minus gamma. And so from this we conclude that AX is equal to twice of phi plus 90 degrees minus gamma. Yeah, so we calculated the arc AX. So now we consider another line. So let's say LB. LB we already considered, so let's say LA. So we connect HA prime with this, so something like this, and we denote the intersection point as Y. And so we will prove eventually that X and Y are the same points. So for this we will calculate again the arc AY now. So to calculate the arc AY, so we employ the same strategy. So yeah, so in this case we have the yeah, so let me increase the picture. So gamma is this angle. So now we have let's calculate this angle. So this angle, so gamma is the external angle to the triangle. So triangle, this one that I highlight in green, right? So in this triangle, gamma is the external angle, so it must be equal to the sum of phi and this unknown angle that we want to calculate. So this angle is then equal to gamma minus phi, right? Gamma minus phi. Then because of the symmetry, because this line, so this line is LA, right? So this line is symmetrical to L with respect to BC. So therefore, like all these four angles, this angle, and this angle, they're all equal to each other. So they're equal gamma minus phi, gamma minus phi, gamma minus phi. So now we have, so now we use this theorem for the angle gamma minus phi, and the two arcs now are, so let me highlight them in red. So this arc and this arc. So this, basically this angle, yeah, I highlighted in red. So this angle cuts two arcs on the circle. So how do we calculate them? So BHA prime. So this is calculated as the inscribed, through the inscribed angle BAH. This angle is 90 degrees minus beta. So therefore the arc is twice that. So let's write this. The arc BHA prime is equal to twice 90 degrees minus beta. Now CY is unknown, or we can write it. So let's write CY, arc CY, as the arc AC minus the arc that we want to calculate. So minus AY. And AC we know, so AC is like there is angle beta that is inscribed subtending this arc. So AC is equal to beta, so minus AY. Yeah, so we now expressed both of these arcs, BHA and CY, both of these red arcs, and so the angle gamma minus phi. So by this theorem, the angle gamma minus phi is equal 1/2 of the sum of these two arcs. So the sum of BHA prime and CY. Now we substitute these arcs. So 290 degrees minus beta. So it's equal to 1/2 of 290 degrees minus beta plus CY is equal to beta minus AY plus 2 beta minus the arc AY. And so from this we express the arc AY. So so notice that 2 beta and 2 beta are cancel each other, So what remains here is 1/2 of 180 degrees. 180 degrees minus the arc AY. So, and from this we conclude that AY is equal to gamma minus phi. No, not gamma minus phi. So it's equal to 90 degrees minus no. Okay, if we multiply by 2, then move AY to the left side and everything to the right side, then it would be 180 degrees minus 2 of gamma minus phi. Yeah, that's what it is. That's what it is, and now we need to compare this result with AX. So AX is AX. Let's rewrite it. So we have it here. 2 multiplied by 90 is 180 minus 2 of gamma minus phi. So this is exactly the same expression. So 180 minus 2 gamma minus phi. This is exactly what we get here. So this is equal to the arc AX. Yeah, so the arc AY is equal exactly to the arc AX. So this means that the point X and Y are the same, and these two lines, LB and LA, intersect on the circumcircle. So from this we conclude that X is equal to Y. We could calculate the arc for the third line. So if we had the third line, LC passes like this somewhere here. We denote this point by Z, and we again we could express the arc AZ and conclude that it is also equal. But from it's actually not needed, because from what we already proved, like because we picked the two lines arbitrarily, like because of the symmetry, like kind of without loss of generality, right? So the same argument works for the third. So like if we consider it, instead of the lines LA and LB, if we consider now, let's say LB and LC, by the same argument, they would also intersect on the circumcircle. So yeah, so so like either we say that for the third line the calculations are similar, or we just say that we picked these two lines arbitrarily, like so without loss of generality. We can say that the same argument works for the third line, for any two other pairs of lines, and this would prove that they also intersect in the same point. Yeah, so this so let's write that this implies that LA, LB and LC intersect at a single point which lies on the circumcircle. on omega. We denote it omega. And this concludes the proof.